In this video, we're going to look at how to sketch the graphs of what are called the Rose curves in polar graphing. And if you look at your reference sheet of the basic polar graphing curves, you can see these two curves here are labeled Rose curves. And something interesting happens with these curves. The equations are in the form r equals a cosine or sine n theta. They both have the same form. If that n value, the coefficient on theta, if it happens to be even, then the number of petals that appears in the curve is twice the number n. And so in this case, this rose curve that we're looking at here, we can see that it has 8 petals. And that means that the equation for this particular rose curve would be 4n because there's twice as many petals. However, if the coefficient on theta happens to be odd, then it equals the number of petals. And so in this case, you can see that we have 5 petals, and that means the equation of this particular rose curve would be a times cosine or sine of 5n. And so we're going to learn how to sketch the graphs of each of these types of rose curves and see why that difference happens. So we're going to start first with the equation r is equal to 5 cosine 2 theta. And just like we've done with previous polar graphs, we're going to graph this using a rectangular axis first of all. So r is equal to 5 cosine 2 theta. This is going to be my r axis. The vertical axis is going to be for r, the radius, and the horizontal axis will be for theta. Now, this 5 in front here, we know that that affects the amplitude of the graph, which means that this cosine graph that I'm going to graph is going to go as high as 5 and as low as -5. But in this case, we have a coefficient on our independent variable, 2 theta. And so this is a new transformation for us in this review of our trig graphs as we've been looking at polar equations. That 2 on the theta is going to affect the period of the graph. Now, a normal period is equal to 2 pi, meaning that it takes 2 pi for us to complete one full cycle of cosine. If I have a 2 on the theta, that means in the normal period, I'm going to complete 2 cycles. And so the 2 is a b value. So my new period is going to be 2 pi divided by that b value of 2, which of course would just be 1 pi. And so if I mark off my theta axis here, pi over 2, pi, 3 pi over 2, and 2 pi, what this means is that I need to complete a full cycle of sine by the time that I get to pi. So I'm going to mark this off in quadrants again, just as we have done with our other polar graphs. We're going to graph this one quadrant at a time. And I'm going to go ahead and mark off my maximum value, my minimum value here. Okay, so the graph of cosine begins at the top of the cycle, which would be up here at +5. And because my period is now pi, that means by the time I get to pi, I need to be back to the top of the cycle. It's going to reach the minimum point of the cycle halfway between those two maximums. And of course, the midline, we're going to cross the midline halfway in between the max and the mins. And so here we have one cycle of cosine, and then, of course, it's going to repeat again. And so you can see that by the time we get to 2 pi, we have 2 full cycles of cosine. So now let's talk about how we translate this to the polar graph. We're going to look just at quadrant 1 angles from 0 to pi over 2. And I'm going to kind of mark that with this red marker. So I notice here that when my theta is 0, the radius is 5. So I'm going to go ahead and plot that point. Theta is 0, my radius is 5, which is on that darker circle there on our polar graph. And when I get to pi over 2, my radius is -5. So here is the pi over 2 spoke of our polar graph. -5 means that I'm going to go down here to -5. I also notice an important point that right here in the middle is where this graph is touching 0, which means my polar graph is going to go through the pole. That, of course, is going to happen at pi/4. I'm going to go through the pole. Now, we could find other points to help us along the way, but if we remember, I mean, we know what this curve should look like. We're getting a rose curve. Well, this rose curve, in fact, our n is even. So our curve should look something like this, although we're going to have fewer petals because our n is equal to 2. But what's going to happen is our graph is going to go like this through the pole, and then it's going to go negative and connect with that point down there at -5 pi/2. And I guess I should have stressed these points right here, notice our radii are negative. My angles here are in quadrant 1. If my radius goes negative, then those points are all going to plot in quadrant 3, which is what happened as I drew the curve there. All right, let's move on to quadrant 2. Between pi/2 and pi, we're going to pick up where we left off at that -5 pi/2. Our graph is going to go back to the pole. So at 3 pi/4, we're going to be back at the pole. And then when I get to pi, we should be out at a radius of 5. So I'm going to start here at -5 pi/2. We're going to go back to the pole. And then at pi, I should be out here at a radius of 5. Now notice my radii are starting out negative. My angles are in quadrant 2. So all of these points are going to graph in quadrant 4. And then once it goes positive, this part of the graph should graph in quadrant 2 because my angles are in quadrant 2. So my rose curve is going to continue this way through the pole, and then it's going to go in quadrant 2 out to our point there at 5 pi. All right, next step is quadrant 3 angles from pi to 3 pi/2. As I go from pi to 5 pi/4, these angles here are positive. So they're still going to graph in quadrant 3, but we're going toward the pole again at pi/4. And then we're going to end up at 3 pi/2 -5. Well, I'm sorry, -5 3 pi/2. So I'm going to start here where I left off. It's going to go through the pole and then end up at 3 pi/2 is my angle, but my radius is -5. So that's going to plot up here. In this part of the graph, it's going to graph positive in quadrant 3 to the pole, and then where those radii go negative, that's going to show up in quadrant 4. And hopefully by now you have a feel for how this graph is going to finish out. My quadrant 4 angles, I'm going to pick up where we left off at -5 3 pi/2, back through the pole right there where we're crossing the x-axis, and then we're going to end up at a radius of 5 once we get to an angle of 2 pi. So we're going to end up back where we started this whole thing. We're going to start this last quadrant, 3 pi/2 -5 is that point up there. It's going to go through the pole, graph here in quadrant 4, and end up where we started. And there we have a rose curve. The coefficient on our input variable was a 2. It's even, and so that means that the number of petals should be twice as many. We ended up with 4 petals on our curve. Now, one of the things to be aware of is when we are doing polar graphs on the AP exam, we don't necessarily have to be able to sketch the polar graph. Sometimes it might be quicker to sketch this graph and use it to help us. And so, for example, if we were asked to find, say, the area of one petal of the curve, well, hopefully you could look down here and find a petal on the rectangular graph. If we notice this piece right here from 5 theta 0 to a radius of 0 at theta equals pi/4, that piece right there is actually half a petal. It corresponds to this part of the graph right here. And if I found the area of that piece, that would give me half a petal, which of course then I could divide by 2 to get an area of a whole petal. Or you might notice that this from here, 3 pi over 4, I'm sorry, radius of 0, theta 3 pi over 4, to radius of 0, 5 pi over 4, that piece of the rectangular graph down here corresponds to this piece of the polar graph right here, which would give us an entire petal that we could find the area of. So what I'm saying is we don't necessarily have to be able to sketch this graph. We just have to understand how this graph relates to the rectangular graph below. And maybe we can just use the rectangular graph to find the information that we need. So now let's look at this equation. R is equal to 6 sine 3 theta. So this time the coefficient on our input variable theta is a 3, which is odd. And what we learned from our reference sheet is that means the number of petals should equal this coefficient on our input variable. We should have 3 petals in this flower. So why do we end up with the same number of petals when that number is odd as opposed to twice as many petals when that number is even? Well, we're going to graph this and find out. So R equals 6 sine 3 theta. Again, that 6 in the front is going to change our amplitude, meaning that my graph is going to go as high as 6 and as low as -6. The 3 theta affects the period. Remember that a normal period is equal to 2 pi. This means that I'm going to get 3 cycles in one period. So I'm going to divide that 2 pi by 3, which means for this particular equation, the period is going to be 2 pi over 3. So I'm going to go ahead and mark this off in quadrants again, because I still want us to think about graphing this in quadrants. But we are going to have to think about our graph in thirds as well. So pi over 2 pi, 3 pi over 2, 2 pi. And I'm going to go ahead and mark those off again. Okay, but before I start graphing, I want to find 2 pi over 3. Now, 2 pi over 3 is going to be just past pi over 2, like maybe right here. This would be 2 pi over 3, which means my halfway point is going to be at pi over 3, which would probably be about right there. We are graphing a sine curve. Sine starts in the middle, so I'm going to start here at 0. It is going to be finished with the full cycle by the time we get to 2 pi over 3. Means halfway through at pi over 3, we should be crossing the midline. In between these first 2 times when we're crossing the midline, sine is going to reach its maximum. And in between these 2 times, crossing the midline, sine will reach the minimum. And so one cycle of sine should look like this. And then we're going to repeat that same pattern. Our next one should end at 4 pi over 3. If I go another 2 pi over 3, I will be at 4 pi over 3, which is going to be about right here. Midway this time will be right there at pi. So I'm going to hit a maximum and a minimum, finishing a cycle by the time we get to 4 pi over 3. And then this last cycle should end at 6 pi over 3 or 2 pi, which would be here. Halfway is here. Maximum at 3 pi over 2, minimum halfway between. This would be 5 pi over 3 and 2 pi. Oh, I think I drew my maximum a little bit too low. I'll pretend that's up there. Okay. So 3 cycles of sine by the time I get to 2 pi. That's what the 3 does for us. So let's look at our first quadrant, angles from 0 to pi over 2. I notice that I'm starting at the pole. We're going to go out to our maximum of 6, back to the pole at pi over 3, and then the graph goes negative. Since I'm in quadrant 1 angles, this part of the graph here is going to graph in quadrant 3. And we're going to end up, once we get to pi over 2, we'll be at -6. So I'm going to plot these points up here. We're starting at the pole. We reach this maximum of 6 halfway to pi over 3, which of course would be at pi over 6. We'll be out here at 6. By pi over 3, we'll be back to the pole, and by pi over 2, we'll be at -6. So here's pi over 2. This point is -6. So I'm going to start graphing here at the pole. It's going to start here, go out to the end of a petal there at pi over 6. It's going to come back through the pole. Whoops. And then remember, once it goes negative, this is going to be graphing in quadrant 3. So this part of the graph is going to come down and meet up with that point right there. And so you can see we've only done 1 quadrant's worth of angles. We already have a full petal and then half of another petal. We're going to pick up at that point right there at -6 pi over 2. Going to cross back to the pole by the time we get to 2 pi over 3, and then reach this maximum point of 6. That's going to happen at 5 pi over 6, halfway between 2 pi over 3 and pi. And then by the time we get back to pi, we'll be back to the pole. So again, starting here at the origin. Oh, no, I'm sorry, not starting at the origin. We're starting at -6 pi over 2. Our first angles are going to be negative. So we're going to graph here in quadrant 4 as we go back to the pole. And then we're going to reach that maximum of 6 at 5 pi over 6. And then it's going to go back to the pole. So we're picking up here through the pole, around through 5 pi over 6, and back to the pole. And as you can see, by this point, we've completed 3 petals of our rose curve, but we've only made it halfway through our graph down here. What's going to happen from pi all the way until 2 pi is that this graph is just going to repeat itself. It's going to graph on top of these same petals. So notice for my third quadrant angles, this part of the graph here is negative, which means it's going to graph in quadrant 1. And then I'm going to end up in quadrant 3, picking up where I left off. This is just going to go right over the graph here, the same part in quadrant 1, and it's going to finish up down here in quadrant 3. And the same thing is going to happen in quadrant 4. We start out positive, so it's going to graph in quadrant 4, but then this is going to finish up last part in quadrant 2. So it picks up here, graphing in quadrant 4, and then finishing up the petal there in quadrant 2. And so technically, if we're graphing from 0 to 2 pi, we really do have 6 full petals here. It's just that on the graph itself, because it's graphing on top of itself, we're only seeing 3.